So we have been talking about chapter 2, and last time we talked about several things. I think we talked about quantum numbers. I think. Remember, there are 4 quantum numbers. There are n, which is really sort of the energy level, if you will, and that runs from 1 through 7. There's L, which essentially will tell you the sort of type of orbital that the electrons are in, and that runs from 0 to n minus 1. Again, all whole numbers as you do that. M sub L kind of tells you really the orientation of those orbitals in 3-dimensional space. It also sort of gives you how many orbitals there are as well. And they run from minus L to 0 to plus L. And M sub L is the spin quantum number, which basically could have a value of either plus or minus 1/2. As we talked about, really, the first electron goes in sort of in the upward spin, which has a positive half. The second electron in orbital, right, goes in the downward sort of orientation, which has the negative half for a spin. And remember that you could really, as we did last time, sort of write quantum numbers for specific electrons and what they are. That led us into the idea really of electron configuration. And remember, you could really create your order of electron configuration by just sort of recreating that chart we used last time. Remember, on the first energy level, based on quantum numbers, there's really only one type of orbital, which is the s orbital. It's not until you get to the second that you see the p's start to develop, not till the third energy level you got the d's, and not to the fourth energy level that you have the f. So if you remember that, sort of go down on a diagonal, you pretty much can just fill in the numbers underneath them, and you'll have the proper electron configuration. You just kind of fill them in. And remember that when we do write electron configuration, we basically just kind of follow the arrows. We always start at the top. And that major sort of difference in the order, as we talked about and we saw, again, is typically the S's, again, do come before the D's. They actually are lower in energy when the electrons are being filled into the atom. As we'll talk about today, to do sort of change in order after you start filling up the D orbitals. Obviously, S orbitals can hold a maximum of 2 electrons. The p subshell, because there's 3 individual orbitals, could hold 6 electrons. The d subshell, because there's 5 different d orbitals, could hold 10 electrons. And the f subshell could hold 14, as there's obviously 7 different electrons there. Remember that when we talk about something like a shell or a level, that's all the orbitals that are on a particular energy level. When we talk about a subshell or sublevel, it's basically the group of individual orbitals that make up, like, say, the 2p subshell. That would be the 2px, 2py, and 2pz orbital that makes up those guys. Remember, orbitals are sort of what we moved to after sort of Bohr's model of that planetary model in orbits to this more probability sort of idea of orbitals as to where we can find a particle like an electron in a particular atom. Remember, the idea of Heisenberg's uncertainty principle is the idea that, as we know more about, say, a location of a particle like an electron, the less we know about how it's actually moving and stuff like that. So again, they do not move in those pretty orbits. They do move randomly about the nucleus. With the idea of sort of de Broglie, it does have wave-like function, and it's sort of tied to the nucleus with that opposite attraction that happens as the nucleus is positively charged, electrons are negatively charged. So right as they're moving randomly, they are still sort of tied to the nucleus through that positive negative charge between them. And they do obviously have wave-type character, which is basically what those orbital basically are, so those probability sort of maps. We also talked about orbital diagram. And orbital diagram is basically when we use boxes or lines, if you want, to represent the different orbitals. And obviously, you would fill in our orbitals, as we go through it. Remember, when we have a subshell with multiple orbitals, they do go in one at a time to maximize the parallel spin before they come back and basically start to pair off. Obviously, no more than 2 electrons per orbital. And the reason they do go in opposite spins like that, which was referred to as being paired spin, is because that allows those 2 electrons not to have the same 4 quantum numbers, which is a violation of Pauli's exclusion rule. So the way they sort of get around that is they are going in opposite sort of spins, and that allows one to have plus a half in terms of the spin, one minus a half in terms of the spin, and they end up with not the same 4 quantum numbers. I think we finished up talking about sort of a shorthand that you could do for electron configuration. You know, if you had 1s2, 2s2, 2p6, 3s2. If we took just this part of it and counted up the top numbers, that is 10. And on the periodic table, 10 is neon. And we can put our neon in brackets and continue on with our electron configuration. Sometimes we produce noble gas configuration, and that is because it should always be a noble gas that goes in the brackets. And noble gases are group 8, where helium, neon, argon, krypton, all those guys are. And that's always what should go in the brackets. And then everybody else just sort of, you just follow up with the rest of the configuration in that particular case. Any questions on any of that stuff there we talked about last time? So the periodic table, which we'll talk a little bit more about, obviously was constructed to allow certain elements that have similar sort of properties to be grouped together. They did a really good job. They left, you know, sort of spaces and sort of filled in the elements along the way. And now we sort of have an arrangement of the elements, obviously, are grouped by similarities in terms of their properties as we go from one to the next. So these are some of the principles we talked about, but another sort of principle in addition to Pauli's exclusion rule and Hund's rule is off-ball principle. And off-ball principle is basically that protons are added basically one at a time to the atom. And that's basically how electrons are added, sort of this build-up sort of process. And electrons, as we talked about, obviously do go into the lowest energy levels first. Orbitals, they fill those up, and then they go to really the next lowest energy level that they can find. And obviously there's our electron configuration for oxygen, which I think we did last time as well. Our 1s2, 2s2, 2p4, bless you. And our Hund's rule, again, was the other rule we talked about when we were doing orbital diagrams. And again, that is the maximum number of unpaired electrons. Basically, all parallel spin is sort of the most sort of stable situation to do that. So the lowest energy configuration for an atom is the maximum number of unpaired electrons. And by doing that, really what that happens is in those subshells where we have multiple ones, the way to get unpaired electrons is that everybody goes in basically parallel to each other until there's really no option, and then they would come back, obviously, and as we talked about, start to pair up. There we go. There's our orbital diagram like we did. I think we did that one last time as well. All right, so let's talk a little bit about valence electrons. Valence electrons are the outermost electrons in an atom. They're the ones in the highest energy level, and they are important electrons, as we'll talk about in the next chapter as well. They're really the electrons that are involved in bonding. And as we'll talk about here in the end of this chapter, they are involved in bonding really because they are the highest energy electrons. They're the furthest from the nucleus, which ultimately means they are not held as tightly as ones that are closer to the nucleus. They're also sort of on the outside, if you will. And so when two atoms come together, it's really those outermost electrons that do come in contact with each other. And that's what really allows sort of bonding to occur. When we look at the electron configurations, for example, here, like our neon here, our 1s2, 2s2, 2p6, a reminder that these front numbers here are the principal quantum number, right? And that's basically the energy level. So what we could see here is, in the case here of neon, both of these guys are on the second energy level, and this guy has 2 electrons, this subshell has 6, and those would be our 8 valence electrons here, those 8. The ones that are lower in energy, these are sometimes referred to as core electrons, and core electrons are the ones closer to the nucleus. They're held a lot tighter than valence electrons, and they are not involved in bonding because of that. They're held pretty tight. They're very hard to sort of let them loose and let them escape. If we looked at our 1s2, 2s2, 2p4, in this particular case here, we have 6 valence electrons, and again, they are both here. We had 1s2, 2s2, 2p6, 3s2. Here, it would be this guy here that would be the valence electrons in that particular case, and that's number 12 there, which is magnesium on the periodic table, and it has 2 valence electrons. So one way that you can figure out how many valence electrons there is simply to write the electron configuration, and then obviously whichever ones are the highest numbers would be your valence electrons. Probably a much easier way to do that is that the valence electrons do equal the group number on the periodic table. And when we look at the periodic table, as we'll talk about in just a second, the group number are the numbers up on top. And we use this representative numbering, 1, 2, we skip sort of that middle part, and then 3 is here and so forth. So the number of valence electrons does equal the group number for our representative elements. And that's a much faster way, obviously, to figure out how many valence electrons are. So if you look at magnesium, it's actually the second group over or column there, and that is 2 valence electrons. Something like sodium would have 1 valence electrons, as it is in group number 1. And then we did neon there at the very end of group 8, at the very last group, and neon would have 8 valence electrons. So much easier way to figure out valence electrons is that it does equal the group number on the periodic table. And again, you could also obviously write your electron configuration to figure it out as well. Any questions on that there? So once again, here is the group numbers, and we do use that A numbering. 1, 2, group 3 is here, and all the way down to group 8. We can actually use the periodic table to sort of count off electron configuration if you know sort of what you're doing. For example, there are 2 groups on the periodic table. First 2 groups here is 1 and 2, and that is the S block on the periodic table. Over here from group 3 to group 8 on the periodic table, that is what is referred to as the P block. And that's because their P subshell has 6, right? So 1, 2, 3, 4, 5, and 6. And here, where our talk about here, the transition metals are D block. They have 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And the 2 rows that are typically on the bottom here are our F block, and they have 14. If you count them all the way across there, you should have 14 little boxes that basically go there. On the left here are the period numbers on the periodic table, and there are 7 periods. And you can basically use the period number as the quantum number as well. So for example, if we were looking at, say, on this one here, we're looking at sodium right here, we would do, this is group period 1. So this would be 1s2 to there. Now this would be period 2. That would be 2s2. This would still be a period 2. That'll be 2p6 to the end. And now we're on number 3 here, and that would be 3s1. So you could kind of count it off if you wanted to. If we wanted to go to chlorine, That would be obviously 1s2 across, 2s2, 2p6, 3s2, and then 3p, 1, 2, 3, 4, and 5. And you can just count it off as well. Now, if you do this, I would recommend maybe not doing this, because there are some places that if you're not sure what you're doing, you will screw up. And the first place where that occurs is actually in our D block, which is between these two groups. So where our transition metals are D block. D's start on what energy level? D's start on the third energy level. So right here, that is 3D, not 4D. So that is actually one back of the period number. So this would be like 4s2, 3d1 right there, and not 4d. That would be 4d here, 5d, 6d, right? Now, if we look down here at our bottom, these two guys actually do go up in this area in here. And that means that this is the 4F, and that would be 5F here. So that's actually 2 behind the period number, because that's period 6 where those guys would normally go. So there are some places, if you try to count it off, you might mess up because of those sort of differences, but you can do it if you want to. I would recommend probably using the zigzag guy. You probably will be good in terms of all your electron configuration. But if you want to check yourself, or maybe do something that's on the outside, maybe not so much on the middle there of the periodic table, you know, it's a good sort of quick way that you can kind of count electron configuration. Any questions on that there? So I think we did a number of electron configurations last time, but let's just look at a couple of these here. Sulfur, which from the periodic table, there's number 16. So again, our 1s2, 2s2, 2p6, 3s2, 3p4. Once again, taking this part of the configuration, which is 10. That is our noble gas that comes right before it, which is neon. In this case, sulfur would have how many valence electrons? It would be 6. It would be the 2 there and the 4 there, which would give us 6 valence electrons. That's barium, which is way down there. And again, if you just kind of back up, a good place where this might come in handy is we can see that xenon there is the noble gas that comes before barium. And we can see there on the outside, barium's on the left, and that is 2N, and that's an S block, and that is 6S. So that's a good way to kind of quickly sort of figure that out in that particular case. In the case here of barium, it would be those 2 electrons right there at the end. That would be its valence electron. It is group number 2. I think you have a different one than this guy as well. All right. So let's talk a little bit about transition metals. Now, transition metals are a little bit different in terms of some things that happen with transition metals. And just so we're clear, transition metals are all those guys that are found between basically group 2 on the periodic table and group 3 on the periodic table. So this is like aluminum, and that is magnesium. And then we have all of our transition metals in the middle, basically group 2 and group 3. Now, transition metals, they have incompletely filled D subshells, or cations that have incompletely D filled subshells. It is right there at the transition metals where you have SC right there, that very first one, where we do get the sort of difference in electron configuration that you might think. A reminder that if you look at our zigzag sort of order that we have the arrows, you will see again that the 4s orbitals are lower in energy than the 3d. And that happens with all these sort of S to D transitions. The S's are lower, the D's are higher in energy. So when electrons get filled into these orbitals, they do go into the 4s first and then start to fill the 3d. As we'll talk about here in a second, what actually does happen though, after you start sort of populating the d orbitals, because they are so close in energy, there's actually a switch in energy that occurs after they get populated. And the 4s actually ends up being higher in energy than the 3d. But in terms of filling order, it does go into the S first and then to the D, and this sort of switches afterwards. And that's why sometimes you may see electron configuration written like in order, where you'll see it go like, 3p, 3d, 4s in order. And that is sometimes usually written, and not in very much in these type of classes, but that's usually written based on energy rather than the filling order as to how electrons go in there. When you write electron configuration, pretty much in all your chemistry classes, I think I only took one where they do it the other way, but you always write it in terms of filling order, which means you should put the electrons into the S's first and then the D's. But in reality, you will sometimes see people write it the other way, and that's based again more on energy after the electrons are in there rather than as they get filled into the atom as they go through it. There is also several sort of exceptions to the electron configuration if you follow that sort of zigzag chart that occur in the transition metal region. Two really common ones that most people talk about is chromium, which is number 24, and also copper, which is number 29. And if you follow that zigzag approach for, say, chromium, which is 24, you would end up with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. So again, if you just sort of follow that zigzag back and forth, for copper, it would be fairly similar to that if you followed it 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. And where the exception sort of comes into play is it's been found experimentally in this region where those orbitals are pretty close to each other in terms of energy, that it is more stable with an extra electron sort of promoted up into the d orbitals on each of these cases. And what basically happens, for example, for chromium is you kind of put an unpaired electron into each of the d orbitals along with sort of the s one. So you got all that maximum parallel spin that we were talking about with Hund's rule, where they're all sort of headed in the same direction. We also will pair up here the copper by doing that. So the correct electron configuration for chromium and copper is here, where we see one less electron in the s orbital, one more electron up in the d orbital. And that happens for both chromium and copper. And to be truthfully honest with you, as we'll see, I think on the next slide, if you go below those two on the periodic table, like where silver is and MO, and kind of go in, there's a lot more very similar exceptions that happen. There's even some that don't have any electrons in the S. They've all been sort of pushed up to the d orbitals. So there's a lot more exceptions, and they're actually kind of right below those guys on the periodic table, chromium and copper kind of coming down and then in. You find a lot of those sort of exceptions that occur. I think we might have maybe some of that here on this. Here we go. So here's a few of those exceptions that we were talking about that where they've found experimentally, there's more stable in this case. So there's the chromium and copper. You can see a similar type of situation here for MO, which again is right below chromium as well on the periodic table, and RU as well. Again, a similar sort of exception. You can see PD actually will shoot up both of those electrons up there and have actually none in the sort of s orbital. So there is a lot of sort of exceptions in that transition metal region, and a lot of that occurs really because those orbitals are very, very close in energy. So, to sort of maximize and stabilize themselves, it doesn't take a lot for an electron to sort of transition from one to the next because of how sort of close and proximal those orbitals are to each other. Any questions on that? I will say for us in most chemistry classes, these are the two you should be aware of and are responsible to know. The exception to the electron configuration, I guess I should circle these, which is the correct ones on that side. You should obviously be aware that there are multiple ones, but we'll just stick with chromium and copper as the two that you're responsible to write correctly. But do be aware that obviously if you're in a book, those other ones will be adjusted differently. So for everybody else, you can follow the zigzag sort of approach and you'll be okay. Any questions on that there? So let's talk a little about sort of electron configuration and also ions. So when we look at ions, which I think we talked about previously as well, there are two types of ions, right? There are cations, which are positively charged ions, and they're results of a loss of electrons. And there are anions, which are negatively charged ions, which is a result of gaining electrons, as we talked about when we talk about atomic number, protons, electrons, and neutrons. Now, when we do have ions, we do have to adjust the electron configuration for the charges that are present. And obviously that's because they no longer have the exact same number of electrons that they started with, as they either gave away electrons or gained electrons. So for example, if we look at sodium here, which is number 11, and we write the electron configuration for it, 1s2, 2s2, 2p6, and 3s1, that being the valence electron that we have for sodium. When sodium makes a charge, they do make a +1 charge. And because it has a +1 charge, it's going to basically lose that 1 electron that is there. And that means that it should only have 10 electrons at that point. And that would be 1s2, 2s2, 2p6. That is the same electron configuration as neon, right? And that's basically neon's configuration as well. Now, if we look at something, say, like sulfur, which is number 16 up there, I think. And sulfur would have electron configuration of 1s2, 2s2, 2p6, 3s2, 3p4 in this case. Sulfur being group 6, again, has those 6 as its valence electrons. When sulfur gains a charge, it actually will gain a negative charge, and it will gain a -2 charge, which means it then should have 18 electrons, which means we actually need to adjust its electron configuration to 1s2, 2s2, 2p6, 3s2, and 3p6 in this case. And in this case, that is 18 electrons are the same electron configuration as argon. Now, when we look at something like sodium with a +1 charge, and we look at neon, they actually have the same electron configuration. They are said to be isoelectronic with each other. And if we look at sulfur with a -2 charge and argon, they also are isoelectronic with each other. And both of those ions that gained a positive charge and a negative charge, they both ended up at a noble gas configuration. And that is essentially what happens with representative elements, and those are guys that are not transition metals. Everybody outside of transition metals, the metals will lose electrons and end up back at noble gas configuration. And non-metals, which are like chlorine and sulfur, they will gain electrons and move forward on the periodic table to the noble gas that comes after them. That is, as we'll talk about in the next chapter, pretty much the basis of all bonding. All bonding is really done to make everybody end up with the same electron configuration as a noble gas, because noble gases are pretty much very stable. And that's what everybody's trying to achieve. And when we make an ionic compound, which is where we get ions from, that is essentially what's happening. The metals will lose electrons and back up on the periodic table to reach that noble gas that comes before them. and the nonmetals will gain electron and go forward on the periodic table to reach the same electron configuration as the noble gases that come after them. It's important to remember that they do not change into those noble gases. They just have the same electron configuration as the noble gas. They cannot change into the noble gases because they did not change any protons, right? So they still have the same number of protons, which means they're still the same elements. They just end up with a much better electron arrangement than they had previously and makes them much more stable. Any questions on that there? Now, that is what happens when we gain ions on our sort of representative elements. It is different in terms of what happens with our transition metals when they gain electrons. So when we look at transition metals, and let's look at our friend iron, for example, here as an example of that. And iron on the periodic table there is number 26. And if we wrote the electron configuration for iron with no charge, it'd be 1s2, 2s2, 2p6, 3s2, 3p6, a little 4s2. And again, you could count over to iron 1, 2, 3, 4, 5, and 6. That's going to be a 3d6. Remember, once again, the s's do come before the d orbitals in terms of the filling process. Now, as I talked about on the previous slide, as they get filled, this is the situation we got going on. And specifically here in the case of iron, we have 2 there, and then we got 6 electrons here, basically. And so that's basically the last part of the orbital diagram there for iron as it gets filled. Once again, once we start populating those d orbitals, we do see that switch that occurs, and our 4s once again here ends up being higher in energy than our 3d. So when something like iron goes to lose its electrons, much like everybody else, it will lose its highest energy electrons, which after we start putting the electrons into the d orbitals actually ends up being the s orbitals. So transition metals are a little bit different in terms of what we take the electrons from. They will actually lose these electrons first. And the difference is a lot of times in how you write the electron configuration, the way that you will write your electron configuration when you get to transition metals is you will not be taking them out of the last thing that you wrote. So you wouldn't be dropping them out of the D's here. You would be taking them out of the S's. Now, in our sort of representative elements like we did over here, you pretty much just grab the electrons or put the electrons in at the end, basically, are the ones that you sort of take them from. But with transition metals, because there's that difference in the energy of those orbitals, we actually end up taking from, obviously, not the end of the electron configuration. So if we had something like iron that had a +2 charge, remember it gained 2 it has a +2 charge, not that it gained electrons. The positive charge means that it lost electrons. So it lost 2 electrons from its neutral, which means it would actually only have 24 electrons present, which means the 2 electrons that will come out are these 2 electrons right here. So these are the 2 electrons that would come out with iron losing those 2. And the correct configuration for iron with a +2 charge would be 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. R, again, because that is argon configuration, argon 3d6 would be the proper electron configuration for iron that has a +2 charge. Now, one thing that you might know about transition metals, and we'll also talk about, is they have the ability to make multiple types of charges. So they can make a variable type of charge. So iron can also make a +3 charge, which is very common, which means it would actually have 23 electrons instead of 26. And when we would go to take out our electrons for this guy, we would still do the exact same thing. We would take those s electrons, but that's only 2 electrons. The next electron that needs to go is this guy, right? That would be our next highest electron. We're now into our D. So you do have to kind of dig into the Ds in this case. And we would end up with 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, our argon 3d5 in this case. So transition metals are a little bit different in terms of how the electrons are removed when they become ions. It is always, for the most part, always the S's come first. If you need to remove more than 2 electrons, then you got to go into the D's and take them from there. We also see here that unlike representative, say, metals like sodium, magnesium, potassium, calcium, these guys do not get back to noble gas configuration, right? They're a little far out still. They can't get all the way back there by doing that. So they actually don't get back to noble gas configuration by losing electrons. Any questions on that there? All right, so why don't you try some here? Let's do nickel with a +4 charge. And let's do phosphorus with a -3 charge. And let's do strontium with a +2 charge. All right, give the electron configuration in case you don't have the periodic table still with the strontium is 38 on the periodic table. What did I just do there? Nickel. That nickel is 28. $208. And phosphorus is 15, the atomic number. Yeah, let's take a look and see. So we'll start with nickel, which with no charge would have 28 electrons to match its atomic number. And in this particular case, it has a +4 charge. So the positive charge means it lost electrons, and 4 is how many it lost. So nickel with a +4 should have only 24 electrons. So once again here, nickel with no charge would look something like argon 4s2, 3d8 in this case. With the +4, we are going to take 2 out of here, and then we would also need to take 2 out of our D at that point, and that would leave us for nickel with a +4 charge if you sort of did noble gas argon, and we should have no s electrons at this point, 3d6. Obviously, you could write out argon's configuration if you wanted to, the 1s2 all the way through there, basically. Any questions on that one there? Yeah. What's that? We do, because nickel's a transition metal. So what happens is, even though the electrons go into the s orbitals first and then the d, once the d orbitals start to get electrons, there's actually a switch in energy, and the 4s actually ends up being higher in energy than the d orbitals. So when it loses electron, always will lose from the highest. So those guys actually go first. And that happens with all the transition metals pretty much. They always will lose those S's first and then go into the D's. Other questions? Okay. So we'll go phosphorus next. Phosphorus is 15. With a -3 charge, that means it should have gained 3 electrons. So it should have 18, which would be 1s2, 2s2, 2p6. 3s2, 3p6. That is 18. That is also argon's configuration, right? It is isoelectronic with argon. Our strontium here has 38, and with a +2 charge means that it lost 2 electrons, which means it should end up with 36 electrons. That would be 1s2, 2s2, 2p6. 3s2, 3p6, 4s2, 3d10. I really should count. I lost track there, but that's 10, 20, 30. So I got a few more to go there, 4p6, I think, in that case. And that is the same as kryptons, I think, configuration. Yeah. Again, we see here the more representative elements end up at the noble gases, or again, transition metal does not. Any questions on how to write electron configuration for ions? Positive, negative. Obviously, you need to be able to do that, right? Okay. Okay, so we're going to then talk about officially the periodic table and different parts of the periodic table. So we kind of touched upon some of it here, talking about this stuff, but let's talk about it officially. Our introduction to the periodic table, that is the periodic table. Obviously, as we talked about earlier, we do look at groups, and when you look at a periodic table, there are going to be different sort of group numberings that you may see. Groups, and if you're really old like me, a family, not too many people call it families anymore, but groups are going up and down on the periodic table. And on different periodic tables, you'll see A numbering, sometimes you'll see B numbering, you'll see just like 1 through 18 as type of numbering. Most of the time in your chemistry classes, and especially in this one, we do use the A numbering, which is the representative numbering. And once again, group 1 is basically here. Group 2 is here. Again, we skip the middle part. That's group 3, 4, 5, 6, 7, and 8 coming across here. When we go left to right on the periodic table, that is a period. And again, there are 7 periods, as we just talked about with our electron configuration, sort of counting off, going in this direction. We also talked about earlier as well, the number above the symbol on the periodic table is the atomic number. That is the number of protons, right, that each of those elements have. And remember, as we saw, it is really the most important thing in terms of what element you're talking about, because everybody has a different atomic number. So no 2 elements have the same atomic number or the same number of protons. So that obviously can identify what element you are talking about. Now, when we talk about different elements on the periodic table, they are broken up into 3 different categories. There are metals, non-metals, and sometimes called metalloids or semi-metals. And on most periodic table, you could kind of see this staircase that kind of starts and comes down through here. And to the left of that staircase, for the most part, and also those 2 rows that are on the bottom, those are metals, and metals are good conductors of heat and electricity. They're malleable. You could hammer them into sheets. They usually have a very shiny appearance. For the most part, metals are solids at room temperature, except for our friend mercury, which is a lot of times why mercury on most periodic tables will be a different color in terms of the lettering. Like blue is very common. Mercury is a liquid at room temperature there. For that element, but everybody else says the metal is usually solid. As you head up and to the right of that staircase, that is where you find nonmetals, and nonmetals are pretty much the opposite of metals. They're bad conductors of heat, electricity. They're dull, they're brittle. The difference, though, is a lot of nonmetals have a much more variable type of state. Some nonmetals are gases, some are liquids, some are solids. A lot of the diatomic elements that we might have talked about earlier on, like H2, N2, O2, Cl2, F2, I2, Br2, these guys, which are elements and come as diatomic molecules, a lot of them are nonmetals, as you can obviously see. Also really important over here, this guy is hydrogen. Yes, hydrogen is a non-metal. Yeah, so even though he's hanging out over there at group number 1, which are metals, hydrogen is not a metal. It is not part of group number 1, but it is over there because it does have some special properties. Years ago, they would actually put hydrogen on both sides of the periodic table. Right next to helium, you would see hydrogen listed again. They don't do that too much, but hydrogen is a non-metal. It's important to keep that in mind as you go through it. Kind of coming down this staircase, that's boron, and some books will include boron, sort of the staircase sort of approach. Those guys there are what are referred to as metalloids, or semi-metals, and you can just kind of see based on their location, they basically have properties that fall on both sides. And what I mean by that is there are certain metalloids that have properties that are very similar to what you find in metals, and they also have properties that are very similar to what you find in non-metals. A lot of semiconductors are sort of in that area, again, because they sort of fall on both sides. The same element will have very similar properties to metals, and also some non-metal sort of properties that go across it as well. And again, they usually will step down. Once again, these two rows at the bottom are metals, and that's because, again, they should go right there. These two guys should go into that spot right there on the periodic table. Now, some elements do have special names. So group 1, which starts with lithium, those are the alkali metals. Again, starting with lithium, not hydrogen. Right next door to it is the alkaline earth metals. And group number 2. And again, most cases, people just call it group 1, group 2, 3, 4, 5. They assume it is A. That most people don't say group 1A, group 2A, or anything like that. Alkaline pretty much means basic is what it means. And that is where we find a lot of strong bases come from. Things like sodium hydroxide, potassium hydroxide, a lot of metals with OH in it. From group 1 to group 2 on the periodic table is where a lot of bases actually come from. All the way over here to group 7 right there, those are the halogens. And those are a lot of those guys that come as 2s, how they naturally come, like the Cl2, Br2, F2. Right next door to it is the noble gases. Noble gases are chemically inert. They are unreactive. They do not react with other things. They'll react with themselves, but pretty much nobody else. As we were talking about, electron configuration is pretty much what everybody wants to achieve, is that nice, stable electron configuration, much like the noble gases. Again, here our groups number being our 1, 2, 3, 4, 5, 6, 7, and 8. And as we talked about, that is also how you can figure out how many valence electrons each of these guys have by doing the group number. The one exception is helium, right? Helium is part of group 8, but it has only 2 valence electrons, and that's because helium only has 2 electrons total, so it can't have 8. So everybody else will sort of follow the group number, but helium is sort of an exception because it only has 2 electrons, so obviously it can't have 8 valence electrons in that case. Now, the 2 rows, as I mentioned before, sometimes referred to as the lanthanides and actinides. And once again, if you follow the atomic numbering, that is really where those 2 guys should fit in. And those are the 2 elements that they should follow through there. Between group 2 and group 3, as we were talking about right here, is our transition metals. And part of what makes transition metals is, again, they can have the ability to make a variable type of positive charge. That is also why these 2 rows on the bottom, which technically do go right there in the transition metal region, are sometimes referred to as inner transition metals, because technically they go in there as well. I've only seen one periodic table ever made like that, and it takes up the whole wall because they have to put those guys in and push everybody to the right as well. Any questions on that there? So you do need to know, obviously, the group numbers, which way they go, the period numbers, where the alkaline metals are, alkaline earth metals, halogen and noble gases, and transition metals are. You obviously need to know what things are metals, non-metals, and metalloids. Any questions on any of that there? Yeah. The last thing we're going to sort of talk about in this chapter is periodic trends. And there's a few different types of periodic trends we're going to talk about: ionization energy, electron affinity, and atomic radius. We will also add electronegativity to it. And the last thing that I want to talk about, I think, today then is actually another sort of guy, which is what is sometimes referred to as Z effective. And that is effective nuclear charge. And effective nuclear charge is the idea of how electrons are sort of held. So for example, if we took lithium, which is 1s2, 2s1, and as we talked about, lithium here would then have one valence electron, right? And these guys would be our core electrons. These are our valence electrons. So if we think about sort of what's happening with lithium, lithium would have a nucleus that basically has a +3 charge, right? Because it has 3 protons. And there would be sort of the first energy level, and for the sake of this picture, I'll just sort of draw them near each other, say those guys on our first energy level. Those electrons would be floating around and sort of very close to the nucleus. We would have some electrons there, or an electron sort of on the second energy level flying around and all that. Now, what happens when we look at the difference between, say, the core electrons and the valence electrons in terms of their attractive force is this. When we talk about opposites attract, positive, negative attraction, it does increase with charge. So something that's like a +3, -3 attraction is going to be much stronger than something that's like a +1, -1 sort of attraction. So when we look at these sort of core electrons here, they are pretty much right on that +3 charge, which means they're going to feel the full brunt of that +3 charge, and it's going to kind of suck them in pretty tight to the nucleus. Again, they are flying around, obviously, but it's going to bring them in pretty tight to each other. Now, when we look at this lonely valence electron, in the case of lithium that is out here, he is actually experiencing something that is referred to as shielding. And what that means is he is actually shielded from the full brunt of that positive charge from the nucleus because there's frankly electrons in front of him, right? There's kind of electrons in front of him. So kind of like when you go to the movie theater years ago, you could pick your own seat. You used to be able to do that, right? So you roll in early, right? You get the nice center seat, right? And right before the movie starts, somebody comes in and sits right in front of you with a giant hat, right? Shields half the screen, right? So you're no longer able to obviously see the whole screen. So same idea here. Those lower energy electrons are sort of shielding the full brunt of that positive charge to that outer electron. You could actually calculate something like Z effective by taking the sort of atomic number minus the number of shielding electrons. So for example, in the case of lithium, the atomic number is 3. And in this case, it actually has 2 lower electrons that are shielding. So we end up with a +1 charge. And that is the effective positive charge that that valence electron is feeling. It's not feeling the full brunt of the +3 charge. It's just the +1 charge holding it there. That is also why that electron is going to be able to be removed a lot easier than those 2 core electrons, because it is not really being held as tightly. So effective nuclear charge, when we think about periodic trends, it increases as you go up and to the right and decreases as you go down. And that is also why, as we go to the right, there are more protons in the nucleus, right? More protons, bigger positive charge, which means because it has a bigger positive charge, all the electrons are all going to be drawn in closer to begin with. And as we'll talk about, that is why when we go to the right and up, the size of the atom is actually much smaller as well, because everybody has a much stronger positive charge bringing everybody in. As you go to the left and down, for example, there's less protons, so it's not going to be able to pull all those electrons in as much, and you get a much larger size in terms of the atomic size. Any questions on that there? All right, we will lay it up there for today.